Good day, students at home. Today we are going to talk about distance time graph. We have looked at distance, displacement, velocity and acceleration. We want to see how we can place the movement of an object on a graph in a graphical form, how we can represent the motion of a body in a graph. We have two types of graph we are going to talk about at IGCSE or O level. We are going to talk about the distance time graph and velocity or speed time graph. These are the two graphs we'll be talking about. But today we are starting with the distance time graph. In a distance time graph, we represent or we draw the distance on the vertical axis. We draw the distance on the vertical axis and we label it in meters. That's the SI unit of distance. And the time on the horizontal axis, and we label it as time in second. That's the SI unit of time. Then whatever information we are given, then we draw on the graph, so that anybody looking at the graph, we know what the graph is saying. The graph will be able to talk. Just mere looking at the graph, you will know what is happening to the motion of that body. There are so many scenarios. There are different scenarios. The first one we are going to look at is a body at rest or a stationary body. A body at rest or a stationary body. For a body at rest, it means the body is not moving, but time is moving. No one can control time. Time must move. But you can control the distance, you can. So, this time around, the body is at rest. That means time is moving, but the body is not moving. Let's look at this graph. Distance on vertical axis and time on horizontal axis. Label it as such. Distance in meter and time in second. Now, if the body is at rest, that means, let's assume we take a reference point. Your home is the reference point. Your home. You are coming to my home. Okay? Some meters apart. Now, I call you at time t equals to 5 seconds. You told me, oh, teacher, I'm still at home. I mark. Michael is still at home. I called you at approximately 5 seconds later. You told me, oh, you are still at home. Oh, Mike is still at home. You called me again 15 seconds, that's 5 seconds later. Mike is still at home. After every 5 seconds, I am calling you and you are still at home. You have not left the reference point. At time t equals to 0, you are there. Time 5, you are there. 15, you are there. It continues every 5 seconds. I keep calling you. You say you are still at home. It means you are stationary. You have not moved from that reference point, your home. So, what will the shape of the graph look like? The graph will surely look like this. A straight line, horizontal, parallel to the horizontal axis. You are still at home. This is what we are going to get. After some hours, I called you. I didn't monitor your progress again. I left you. Then I called you after some time. Where are you? Or let's forget about this. It doesn't just have to be like this alone. Anything horizontal to this axis, to the horizontal axis, that is to the time axis, is anything horizontal to the time axis is a body at rest. It can be here, it can be here, it can be here, it can be anywhere. Maybe the first time I called you, where are you, Mike? Time t equals to 0. Mike, where are you? I am at the petrol station or at the train station. At time t equals to 0, I call you. Again, at time t equals to 5 seconds, I call you. I am still there, teacher. I called you again after 5 seconds. I'm still there, teacher. Every 5 seconds I call you, I keep calling, you are still there. If you are there, your distance is not increasing, but time is increasing. It means you are at rest. You can see it is still horizontal. It is still horizontal. It is still the same. It is still parallel to the axis we are talking about, the horizontal axis. So once you see a shape like this for a distance time graph, any line that is parallel to the horizontal axis shows that that body is at rest. So a body at rest. This is for a body at rest or a stationary body. You can see it is parallel. Please make sure this axis is distance. Please don't make that mistake, because if this axis changes, the meaning of this horizontal line will change. For a velocity time graph, it is different. The same shape but means different thing. But for this, if it is distance against time and you see horizontal line like that, it means it is at rest. Next, let's look at a body, number 2. Let's look at a body moving with uniform speed. A body moving with uniform, steady, or constant speed. We talked about different types of speed. We are drawing distance time graph, and the teacher is talking about speed. Yes, you will know the reason now. This is distance in meter, don't forget that, and time in second. If I have in 2 seconds, this guy has moved 10 meters. In 4 seconds, has moved 20 meters. In 6 seconds, has moved 30 meters. So in 2 seconds, he has moved 10 meters. In 4 seconds, he has moved another 10 meters. In 6 seconds, again, another 10 meters. That means every 2 seconds is moving 10 meters. So 8, he has moved 40 meters. He has moved 50 in 10 seconds. And in 12 seconds, this guy has moved 60 meters. That means you can see every 2 seconds is increasing its distance by what? By 10 meters. Every 2 seconds is increasing its distance by 10 meters. That means it doesn't move faster than it started. You notice at the beginning, its speed has been the same. If in every 2 seconds its speed increases by 10 meters, that means every 5 seconds every 1 second its speed its distance increases by 1 meter. If its distance increase by 10 meters every 2 seconds, that means every 1 second its distance increase by 5 meters. So that means it did not increase its speed. It continued with that speed. That is why we see constant speed here. So this is a body moving with constant speed. That's second scenario. With constant or uniform speed. Constant speed. Write that down. Or uniform speed or steady speed. A body moving with constant speed or uniform speed or steady speed. So the shape of that graph will be that of a straight line passing through the origin. If I want to draw my graph now, I'm going to draw something like that. You can see line of best feet. You see that this is a line. You can see it's a straight line graph passing through the origin. Once you see a straight line graph like this, okay, it is angulated like this, you know the body, it does not curve, it does not change, the steepness does not change. What do I mean by steepness? Steep. The steepness does not change. You know that this body is moving with uniform or constant speed. How do you now get the speed from this graph? That is one question that is common also in exam. How do you now calculate the speed from this graph? I can calculate the speed from this graph by taking the gradient. The gradient. Okay, I take the gradient of the graph, of the slope. Gradient means I draw a right angle triangle as big as possible. I always like using the whole thing. I call this rise and I call this run. I call this rise as in your mathematics and I call this run. My rise is from 0 to what? 70. It's from 0 to 70. Let me limit it to what I have in my graph. Let me use from 0 to 60. Okay, you can see it's big enough. It has to be big. Don't choose something as small as this. Yes, you get the same answer, but sometimes it will not be accurate. Okay, the bigger, the better for you. So let it be as big as possible. So my rise now is from 0 to 60. This line. So that is my rise. And my run is from 0 to 12. My run. So you say speed equals to gradient, which is equals to rise divided by run, which is equals to, you see, vertical divided by horizontal. So which is rise is change delta, distance, change in distance, and run is delta t, change in time. So which is equals to delta d divided by delta t. You don't have to write this if you don't want it. So which is 60 minus 0 divided by 12 minus 0. This is going to give you 60 divided by 12. 60 divided by 12, it is 60 meters divided by 12 seconds, because 12 is horizontal. So this gives us 5 meters per second. 5 meters per second. These 5 meters per second represents your speed. You can see this is in meter and this is in second. It represents the speed. That speed is uniform. That means every second you move 5 meters. So that is your speed. This is the second scenario. This is the second scenario. Let's look at another scenario. This one now is moving away from a reference point like that. Let's assume it's moving backward to a reference point. Backward to a reference point. A body moving backward. A body moving backwards. A body moving backward. A body moving backwards. If the body is moving backward, what do we see? Again, vertical axis and our horizontal axis. Our distance in meters, our time in seconds. So, what are we going to see? That means at time t equals to 0, it was at a point far from the reference point. Maybe at time t is equals to 0, the reference point, let's say, is your home now, and I'm coming to your home. I'm coming to your home. At time t equals to 1, t is equals to 1, at time t is equals to 0, I am in your home. Time t equals to 1, I am at a point, and your home, maybe it is, let's say, 50 meters away, 40, 30, 20, and 10. At time t equals to 0, in your home, coming to my home. My home is the rest. I'm in my home, sorry. From your home to my home is 50 meters. So your home is the reference point. So after time t equals to 0, I am in 50 meters away from the reference point from your home. Time t equals to 1, I am now at a point 40 meters away. Time t equals to 2, I am at a point 30 meters away from your home. Time t equals to, you can see the distance is reducing because I'm coming back, moving backwards to your home, to the reference point. So at this point, 3, I'm at 20. And at 4, I am at 10. And at 5, I reach your home. At 5, I reach your home. At time t equals to 0, when I'm about to start the journey, I was 50 meters away from your home. Time t equals to 1 second, 40 meters away. Time t equals to 2 seconds, I'm 30 meters away. Time t equals to 3 seconds, I'm 20 meters away. Time t equals to 4 seconds, I'm 10 meters away from your home. And time t equals to 5 seconds, I am at your home, 0 meters from your home. So you can see I have moved backward to the reference point. I have moved backward to the reference point. I have moved backward to the reference point. I move backward to the reference point. So once you see something sloping down like this and it is straight, it is for a body moving backward. You can also calculate the speed with which it's moving backward. Just rise against run. It doesn't have to be negative, it is positive. Rise against run, because speed is never negative. Rise against run. So that is the speed, which is 50 divided by 5. which is 10 meters, every second you are moving backward 10 meters. So for a body moving backward, this is the graph. Body moving backwards. To a reference point. So moving backward. For a body moving backward, this is what you see. Okay? It's for the shape of a graph of a body moving backward. Now, let's go back and look at. Now you can get the speed. We have checked for the body moving with uniform speed. We have checked for the body at rest, and now let us now look at the different speeds. Can speed be different? Yes. If two bodies are moving, two of them have different speed, that means the slope will be different. The gradient of the slope will be different. If you have different speed, if I have body A and body B, body A and body B and body C, three of them moving, A, B, C. Body A is a white body, body B is a brown body, and body C is our green body. So these three bodies, they are moving with straight line, uniform speed. Straight line, uniform speed. Straight line, uniform speed. But the speed of one is highest here. The one that has the highest speed is the one that has the steepest slope. The slope that is the steepest. Steep, gentle. Steep, gentle. This is steep, this is gentle. This is the most gentle slope, and it's the least steep slope. The most gentle slope, but the least steep slope. When the slope is steep, the steeper the slope, the higher the gradient. The steeper the slope, the higher the gradient. The steeper the gradient, the slope, the higher the gradient. And don't forget, the gradient here represents what? Speed. So which guy is moving fastest? A is moving fastest, followed by B, followed by C. So speed A, speed of A is greater than speed of B, and B is greater than speed of C. C has the least speed here because this is the steepest, followed by this, and this is the most gentle of all. So now, what if a body starts? What if a body starts, and that body starting has distance here in meters and time here. Let me just draw it as sketch this time. I don't want to go into the grid again. It doesn't really matter. I have the body moving like this initially, starting like this initially, then the body move like this later, then the body move like this later, then the body move like this later. What does this tell me? It means when you look at this, it's a straight line graph. It's a straight line. It means it's moving at uniform speed. This is also a uniform speed, and this is also a uniform speed. But these three uniform speeds are different. Look at it. This and this have different steepness. This and this is more steep than this. So this is a faster speed. The speed here at A, the speed at A is greater than the speed at B. And the speed at C, how can we know if it is the same speed as A or different from A. The only thing we can do is to try to extend the line, try to extend our line and see. Is this line parallel to this line? If they are parallel, it means they have the same speed. If they are not parallel, that means they do not have the same speed. Let me draw something better. I don't want them to have the same speed. I don't want them to have the same speed. Okay, I don't want them to have the same speed. I want one speed to be different from the other. Okay, my A already known that my A has a higher speed than B because it is steeper than B. B is more gentle, became gentle. It was moving at high speed, then it slowed down. Then again, when you look at the slope, it is steeper than this. So it moved even faster at point C. At C, A faster than, it was moving faster than B, and C is the fastest because it is the steepest slope. So the slope, the steepness of the slope tells you what the speed is. Here, there is no slope at all. When you look at it very well, it's like there is no slope there at all. Let me draw it well. At that point, there is no slope. We have seen A, we have seen B, we have seen C, D. There is no slope at all. What does it remind you of? It is parallel to this axis, to the horizontal axis. It means it's at rest. It stopped. It stops. It stopped. It's at rest. Time is moving, but distance is not moving. So that is to tell you that this is here moving fast, slow down, moving fastest, and not moving at all. Another thing we can look at is this. We can change it to a curve. If I draw this and curves it there, it changes to a curve. That means at that point of the curve, I have changed my speed. Okay? So because speed most of the time don't just change suddenly like that. So what we have, you see, it was moving uniform speed, then it was moving uniform speed, then decide to change the speed, gradually decide to change the speed. You can see it curving, then became straight again, then about to change the speed again, curving, then became straight again, then curving, then became horizontal. So most of the things we have in life is like this in real life situation. So here is moving at uniform speed because it's a straight line. Here you start changing. At this point, it started changing the speed because it started bending down. So it started reducing the speed. At this point again, where it is straight, it has uniform speed or constant speed again, okay, but lower than this. Then it started changing at this curve. Then it became straight here again, uniform speed. Then it started changing here and became zero. This is in most cases in real life. You don't just change suddenly like that. Okay? It takes time. So that's why sometimes you have curves in your exam. So when you have curves in your exam, it's still the same thing as what I drew earlier. Same as what I drew earlier. So now, this is for body moving with changing velocity, of changing speed. You can see the speed change when the speed of a body is changing. You have seen that before. Somebody will say, teacher, we are talking about distance against time. We are talking about speed, because speed is important here because it is the gradient of distance against time. Once you are plotting distance against time, the gradient of your graph at any point will be the speed. When there is no gradient, that means it is not moving, it is not speeding, it's not moving at all. No speed, zero, horizontal, parallel to the horizontal axis. Now, this aspect I want to describe is for Cambridge students. Even the changing speed stuff, mostly for Cambridge students, not Edexcel. For Edexcel, you come across this in grade 12. If I have a graph like such, distance against time, my distance in meters, very important, and my time in second, very important. And I was moving like this. What does this graph tell you? The graph tells you that initially I was moving with, look at this gentle slope. Then I started changing the slope here, started getting curved here. And when it got to this point, it became straight. Here, it was very gentle. It getting steeper, it became very steep here. This body changing speed. It was moving slowly before, then it started moving faster. This is the shape of a graph with changing speed. This changing speed, is it increasing speed or decreasing speed? Look at it now. Gentle, low speed, steep, high speed. So that means it moved from slow speed to high speed. That means this body accelerated, speed up, increases its velocity, increases, accelerated, increases. So because when you do it this way, you will see a slow down, a slow here, low speed, and high speed. Somebody may ask you to find the speed of the body at any point on a curve. These points, let's assume I have 1, 2, 3, 4. And 10. 5, 10, 20, or 15, 20, 25, and 30. I have this. And somebody is asking you to find the speed at a curve. If you are asked to find the speed within this area, now it's easy for you. Rise against run because it's straight. But what about this area where it is curved? Somebody is asking you to find the speed of this body at a point where it is curved. At this point, it's a curved area. Then don't be scared. You just draw what you call a gradient in mathematics, a tangent in mathematics. That is what you call a tangent in your mathematics. Draw a line tangential to that point, touching that point, and use that line to form a right angle triangle. Be very careful. Be very careful. Make sure that line touches that point. Let me make it big. Look at my line. Make that line the hypotenuse of a right angle triangle. I made it the hypotenuse of a right angle triangle. I form a right angle triangle with that, and I made it the hypotenuse. I made it the hypotenuse of the right angle triangle. I forget about that point. I have used that point. What do I need that point for? I only need that point to draw my tangent. That tangent, make sure your pencil is sharp enough that your tangent is touching the line at that same point. You can see that of your teacher is not very accurate. For you, your sharp pencil should touch at that point. Okay, somebody asks you, calculate the speed of this body at 4 seconds. So, you move to 4 seconds, from 4 seconds, you touch the slope, then you drew a tangent at 4 seconds to touch the slope at that point alone. So, you again do your rise against your, divide by your run. Rise of your triangle, divide by run of your triangle. Same triangle, this big triangle, you have no business with the curve again. So, my rise now is from 0 to 17.5, that is 17.5, this place is 17.5, this part is 17.5, that's the tip of my triangle, minus the base of my triangle is at 0, divide by, what about the time? From 2 to 9. So 9 minus 2. 17.5, that's my rise. Divide minus 0. Divide by my run, 9 minus 2. So I have 17.5 divided by 7. 17.5 divided by 7 from our calculator. 17.5 divided by 7. It gives us 2.5 meters per second. It gives us the slope to be 2.5 because this is meter and this is second. So we have 2.5 meters per second. This is the speed at this point. If you check at another point, it will be different because it's a curve. Speed at every point in the curve is different. But for this straight part of it, the speed is the same. Once you can get a straight part of it, the speed will be the same. So for this body, you see, this is the graph of an accelerating body. An accelerating body. This is the last scenario. This is the graph of an accelerating body. So we have the graph of an accelerating body. We have the graph of a body moving with uniform speed. We can tell which speed is fast, is more. And we can tell when a particular body is changing speed. We can tell by looking at the slope, the steepness of the slope. When is the slope changing? Is it becoming steeper? Is it becoming more gentle? So if it's becoming steeper, it's speeding up. If it's becoming less steep, or it is becoming, it is slowing down. So, and we also know that the body of the graph of a body moving with uniform speed just like that, we know that of a body at rest. We know that of a body moving backward from a reference point. We have seen all these graphs. This is what you did with distance time graph. Distance time graph, distance time graph. For now, it is no more than this for you. So you can see an accelerating body moving the curve gentle before becomes steep. And you can be given a decelerating body, a body decelerating, a body that is decelerating. That means the curve, distance against time, distance in meter, that means the curve was very steep before, then it becomes gentle. It becomes gentle, opposite of that. So it was steep before, high speed, it started slowing down here, slowing down, then slows down, so low speed. So it decelerates. So it decelerates. So decelerating body. Decelerating body. So when you can, and you can get the gradient the same way Tangent, at any point, they'll tell you at what time. You give it the time, you check the time, put your ruler, use the time, your ruler to touch that point, the time, and your slope. Then draw a tangent. Draw your tangent there. Draw your straight tangent there, and of course, you rise, you run, and get the speed at any point. It may be here, it may be here, because it is. You can see decelerating body is exactly opposite of accelerating body. Slow, moving slowly, low speed, changing the speed to become high. It became high. But the other one, moving at a fast speed at the beginning, slowing down, it goes like that. So you have seen a lot. Distance time graph can come as a body at rest, flat. It can come as a body moving with uniform speed, straight on like that, sloping. And the speed, you can know when the speed is high, when the speed is low, by looking at the steepness of the graph. Again, you can compare the speed of 2 different bodies or 3 different bodies looking at the steepness of the graph. When the graph is steep, then the body is moving very fast with high speed. When the graph is gentle, the body is slowing down, low speed. And you also know that to get the speed, you need to look at the gradient of the graph. Okay? Now, if a body is accelerating, the curve will be gentle at the beginning, then it becomes steep. That means gentle, then steep. If it is decelerating, steep, then gentle. And you know the graph of a body moving backward to a reference point, it slopes down. It slopes down. So this is easy for you. This is easy for you. So this is all you need for IGCSE. If you have any question, you sure let me know. And I will send back a reply to you, your answer to you, in form of another video custom made for you. This is where we are different from other platforms. Good day and God bless.